In this question, we're thinking about the breaking strength of ropes that are being manufactured by a company, right? And so what we're saying is that we tested 6 of these ropes. So we'll take n equals 6, right? And the average breaking strength among those 6 was 7,750, right? 7,750 as our mean. And we observed a standard deviation here of 145. Okay, so this is our observed data. The manufacturer claims that the mean breaking strength is going to equal 8,000 pounds, right? So according to the manufacturer, we're in this position where the mean equals 8,000 pounds, right? And the question is, do the data contradict the manufacturer's claims, right? So where are we with this? How do we go about testing this? First thing that I'm going to say is that to begin, let's start with testing this hypothesis that we have equality. In this case, you might not care about the two-sided hypothesis test, right? You might not care whether the mean breaking strength is actually larger than the rated 8,000, but maybe you do, right? Maybe you don't want to be using ropes that have too strong of a breaking strength either, right? So perhaps being actually close to what's being rated is important to you. So we don't care about deviations just below or just above. We're just going to test this. What that means is that our alternative is going to be equal to mu not equal 8,000, right? The other piece here that I'll note is that we have n equals 6 individuals. Right? Because we have n equals 6 individuals, we can't use the central limit theorem here. And so what we'll need to be able to assume is that we have normally distributed data, right? Because if we don't have normally distributed data, then our sample size is too small to assume that it's going to be approximately normal. And then we don't have a technique for actually doing this, right? So what I'll come in here and say is that we want to assume normality. And of course, given what we know about this question right now, we don't know whether this is going to be a reasonable assumption. In practice, you could actually go about trying to test this or say plot out a nice QQ plot, probability plot, to determine whether you think that this is a reasonable assumption or not. But for our purposes here, we'll make this assumption because otherwise we can't proceed in the question. So once we've decided that, we would need to come up with an alpha level, right? And again, alpha is probably going to be something like, say, 0.01 in this case, right? Depending on the use for these ropes, you might actually want to even go sort of to a stronger alpha level, right? 0.001, for instance, in order to make sure that you're actually getting the correct ropes, right? It depends on what the ropes are going to be used for, depends on how important it is to not make these, right? But so again, we'd want to justify this based on how important is it to get these right. And once we've done that, we're going to be thinking about actually working out our observed statistic here, right? And so what we'll do is we'll take x bar minus mu naught. In this case, we're going to have s divided by the square root of n, right? Because we don't know the population variance. And so if we actually plug in our values here, we observed a mean of 7,750. The rated claim is 8,000. The standard deviation that we're observing is 145. And there were 6 individuals. So divided by the square root of 6 there, right? And once again, you can sort of compute this using your calculator at this point. And that's going to be equal to negative 4.22 if you do this. So the thing that I'll point out right now, and perhaps you have sort of the intuition built up about this at this point, perhaps you don't. If we had this being a standard normal sampling distribution right now, then this negative 4.22 is going to be way less than the critical value, right? So sort of immediately, using the normal intuition here, we could conclude that this is going to be significantly different. And that would make some sense given that we've observed this 750 rather than sort of up to the 8,000, right? So intuitively, we're thinking, oh, this probably is not going to be something where we can accept that the null hypothesis is reasonable, right? We almost certainly have lots of data against the null hypothesis here. But the important thing to remember is that in this case, if the null hypothesis is true, so if H naught is true, then what we're going to have is T following not the standard normal distribution, but instead a T distribution with n minus 1 degrees of freedom. So that's going to be with 5 degrees of freedom, right? And so it's important for us to, again, plot out what's the scenario that we're in right here, right? So we're going to have this sort of approximately bell curve shaped distribution. And we've observed something that's negative 4.22. And remember, our null hypothesis is that the mean is equal to 1800. So if we ask what constitutes evidence against the null, either values that are down sort of more extreme negative, or we want to consider values that are going to be above 4.22, right? And so then in this case, what we want to know is the probability that you fall into either of these tails here, right? And so to take that, we're going to say that the P is going to be the probability that we have our observation, and let's just call that T, is going to be less than or equal to negative 4.22 plus the probability that this statistic is greater than or equal to 4.22, right? And in this case, we're thinking of T being the T distribution with 5 degrees of freedom. Now, each of these probabilities is going to be exactly the same because the T distribution is symmetric about 0, right? And again, we're not actually going to ever be computing these probabilities by hand. Instead, we'll rely on software or on tables in order to find those. But this is our distribution coming from a T5 distribution. And if we figure that out, if we actually sort of use the software here, what we should find is that each of these probabilities is going to be approximately 0.0042. So, right, and so we'll get that plus 0.0042. And so then in total, we'll get 0.0084. Right? And so now what we have to do is actually draw our conclusions, right? And so now it's going to depend on what alpha did we choose, right? Because if we choose alpha equals 0.01, right, then of course 0.0084 is less than 0.01, and so we would reject the null hypothesis. But if we needed certainty at the level of, say, 0.001, right, now suddenly we wouldn't be rejecting the null hypothesis. We'd fail to reject the null hypothesis. And so here it's going to matter what significance level we actually choose. It's going to be hard, sort of without context, to come up with the exact significance level that we would need here. But it's important to realize that because we have such a small sample, right, because we're dealing with only n equals 6 individuals, while this looks on the surface like it's going to be something that we can very immediately reject, right, this difference of 250 is sort of not that big comparatively speaking to the standard deviation that we're actually observing, especially because we're only dealing with 6 individuals, right? And so here it's not as clear-cut as some other cases where we have a lot more individuals, we can get that variance down and then sort of be much more firm in our conclusions. So here, whether or not you say that you're going to reject the null or fail to reject the null is going to come down to which alpha you've justified. And then from there, you can decide, is this something that you actually care about, practically speaking?